let me introduce the speaker. It will take me about 1 hour to do his whole bio, so I will not do it. So I'm very pleased that we have Dr. Leszek Demkowicz here. He's my former advisor at UT, currently a full professor at the Department of Aerospace Engineering and Engineering Mechanics at UT, full professor at the Department of Mathematics, and he is a member of, he's a co-chair of the Oren Institute.
Assistant director.
Assistant director.
It's nothing. I used to say assistant to the director.
Assistant to the director.
It's a change a little bit over.
Okay, so I'm not going to go through the whole bio. I'm just going to say he's expert in high order methods, more recently DPG methods, and he also awarded the Computational Science Award at USACM 2009. I think you're going to talk today a lot about some DPG and some functional analysis and numerical analysis and some eigenvalue problems, and be prepared for
a lot of mathematics.
A lot of mathematics.
Thank you. So 2 weeks ago, I had to listen to about 30 presentations one day, and I'm going to take it back on you guys. So thank you for mathematical ride. I've been told that I should not and I don't have to avoid mathematics, but just hit it on. But I'm going to do some introduction. So Stefan is online. This is his work. You're looking here at the simulation of optical amplifier, in simpler words, laser, right? Mathematically, that is the solution of two nonlinear time-harmonic Maxwell equations representing the signal and the pump coupled together with each other and coupled with a transient heat equation to account for thermal effects. So it's a non-trivial problem. But the first and the foremost non-triviality here comes from the fact that this innocent looking picture here representing what is called transverse mode instability represents solution of Maxwell equation with not less than 10 million wavelengths. And we're talking 3D simulations, 10 million wavelengths, right? So we did start about 6-7 years ago with a modest 500 wavelengths on actually less than 80 wavelengths on the workstation. Then with some optimization that Stefan did to the code, we were still able to get to about 500. This is where openMP came in, that Socrates implemented into a code, after which Stefan worked for 2 years on his PhD dissertation, which was to develop an MPI/openMP version of the code, which he did. And there, we were, with that code and multi-core architectures, we were able to go all the way to about 20,000 wavelengths in 3D Maxwell. So that itself is already quite remarkable, but for that you need a supercomputer. So I'm going to tell you how we went from 20,000 to 20 million right today and the mathematics behind that. But before we go into this, I've been told that I should do a very short introduction to DPG. So there are several DPG people here in the room, so I don't feel like I have to go very deeply into details, but let me give you some very, very quick overview. So it all starts with the variational theory, right? And here's the famous Babushka-Nechev theorem. And if you switch from the, by the way, for the online audience, I'm using a traditional pointer because for some reason the mouse doesn't work. I mean, when in the full screen mode. So here's a traditional variation problem and the famous in-soup condition of Ivo Babushka and the compatibility condition. If you translate that into the operator statement, that you're looking at the closed range theorem of Banach. So Babushka-Nečas and then Babushka theorem is nothing else than the restatement of the classical closed-range theorem of Banach. It's not that I'm not giving credit to them. There is a huge credit to connecting between the different communities, but the mathematics originates there, right? And then, you know, there's a Petrov-Galerkin method, discrete version of it, and the famous Babushka theorem. You simply add the letter H. Oh, it's really warm next to the screen. And under the assumption that the trial and the test spaces are of equal dimension, so you end up with their square system of equations to solve, the continuous discrete in-soup condition is replaced with a discrete in-soup condition, right? And under that assumption, you have existence of a unique solution. That's not a surprise. It's a particular case of the previous theorem. But additionally, you have the famous result of Ivo Babushka that the approximation error is bounded by the best approximation error times the stability constant. Ivo actually proved a weaker version of the theorem with 1 plus. This was later improved by Nikatanov from Penn State, who removed 1. I learned it at least from him, right? And the stability constant involves continuity constant for the binomial form and the discrete in-soup condition. The bound is below constant. So if the discrete in-soup constant is the question is bounded away from 0, then this thing is bounded above uniformly in H, and the method will converge at optimal rate. So, you know, that's what I teach. And then one of the first things that you teach very quickly is the Bretzi theory, the mixed problem, right, representing or originating from constraint minimization problems. And one of the unpublished papers, reports that I wrote about 20 years ago, has huge citations. It's called Babushka equivalent Bretzi. And there I make the big point that you don't have to be ingenious like Franco was, but if you rephrase the Bretzi mixed problem as a standard variation problem, with the group variables U and V and the group bilinear form, and then the in-soup condition for the rephrase standard variation problem. So we're talking here again at a continuous level, Banach-Babushka, right? Nečas on the continuous level, Babushka, on the discrete level, Babushka. That is equivalent. So there's implication in both directions to the two conditions of Bretzi. The actual, what is called Babushka-Bretzi or Ladezhenskaya LBB condition, right? The discrete version of it, and then the in-soup kernel. So, in a sense, you might say that, you know, without going into details, that Babushka implies Bretzi. But with DPG, the story is that also Babushka is a special case of Bretzi. Not only Bretzi is a special case of Babushka, but Babushka is a special case of Bretzi. What do we do? Well, if we look at the equation again in the operator form, we introduce the residual. The residual is 0. And if the residual is 0, then you introduce the Riesz representation of the residual here in the Hilbert space setting, right? And that psi is 0 as well, because the residual is 0, then the Riesz representation of 0 is 0, right? And if the psi is 0, then you can add any equation you like. So how about if we add the equation by prime equals psi equals 0, and then this system is equivalent to a mixed problem where your original unknown becomes now the Lagrange multiplier, and you have additional unknown, which at the continuous level is 0. Right? This is one way to introduce what we do in DPG. It's one of 3 ways to the mixed problem. Actually, it wasn't invented by me. It was invented by Wolfgang Dahmen and his collaborators 2 years after Jay and I published our DPG papers. 2 other, formulations are based on minimum residual or optimal testing. So you have Jamie here, you have Socrates, they know all the details of it by heart. So instead of discretizing this original problem, we discretize the mixed problem. And if you look now at Bratzy conditions, that the in sub in kernel is trivially satisfied because this is inner product, so the in sub in kernel constant is actually equal 1. And the Babushka-Bratzy or LBB condition seems to be exactly the same as the original in sub condition for the bilinear form. So when you look at it, the first time, and say, so what the heck have we gained? I mean, in the end, we still have to solve to satisfy the in-sub condition, right? So this is the first question for the audience. What have we gained? Have we gained anything? And the examination for Socrates and the quiz. Well, what you have gained is that you are no longer bound to have the same dimension for U and V. Right? In this setting, U and V have to be in the same dimension to get the square system. Here, because you're solving a large system in a mixed method terminology, right? I mean, formalism, that the dimensions of U and V do not have to be the same. They can be different. And therefore, by pumping up the dimension of V, intuitively you can see right away that it will be much easier to converge with the discrete in-sub constant to the continuous one. You're going in the right direction. I think this is a very powerful intuition to understand why it works. You're simply testing with more guys, and on top of it, you have here this additional information psi. We, instead of calling that Rees representation of the residual, we call it originally error representation function, and the name stuck. So we are stuck with it. So that's the main idea. Very simple, right? I mean, after you know what is going on, it took us a few years to learn that. So now a little bit about the implementation. And the implementation here, okay, if you discretize it, right? This is the discrete form of it on top of the original stiffness matrix that now is rectangular because you're testing with more guys, right? You have its adjoint right here for the conjugate, and you also have the ground matrix corresponding to this problem. If you eliminate psi h, you get this system of equation for the original unknown u, which very much resembles least squares if G is identity matrix, right? But the difference and the generalizations is extremely powerful because choosing the right G is the whole part of the story, right? So the big point is that you can apply this technology to any well-posed variation formulation, and given the fact that one and the same problem can be formulated in many different ways. For instance, classical acoustics equations, you have 6 formulations, Maxwell 6, elasticity 6, and so on. You choose the one that fits the best the stability properties you want to see, right? And you choose the one that is easy to discretize. So, in other words, the energy spaces involved are easy to discretize. You don't stand on your head and try to discretize very difficult energy spaces, like, for instance, H-zip sim for elasticity. I'm sorry, I don't want to get political. This is a great area of research, and many people are involved in that. But from the practical point of view, for me, this is like standing on your head and trying to be efficient there. It's really difficult, right? So that's what we do. And then comes the big point that I will not go into right now about breaking test functions, testing from a larger spatial test function, which make this matrix G block diagonal, and this entire inversion process is taking place on the element level. So here comes the efficiency, right? We do extra work to compute those normal matrices, but all of this DPG magic is happening at the element level, right? You pay the price though, and the price is because you're breaking test functions, there is a corresponding Lagrange multiplier, and this is identified as a trace. You have additional trace unknowns that come from literally discretized with traces of proper energy space. So I'm going to quick now this part of presentation and go to the actual topic. And in the end, I will have a small commercial yet on some other work that we're doing right now. All right, so I will start with DPG fundamentals. We already have talked a little bit about that. In context of wave propagation, we are using what is called the ultra-weak variation formulation. Ultra-weak variation formulation is based on the system of first-order equations, AU, but instead of using least squares on that will lead to fossils, right? You multiply with the test function and you integrate by parts. You move all the derivatives into V, hence the name ultra-weak. We stole the name from Sessenat and the spread. And when I confessed about that to the spread, he said, that's all right, we stole it from Lyons. So the name has been in use already for some time. Right? And this is what is we call the ultra-weak formulation because the energy space for you is L2, right? Now, if you're solving high-frequency wave propagation problems, then you learn after a while that all that matters is the waveform. That means you want to use the weakest norm possible, and that's L2. And if you open the dissertation earlier of Jamie, and then first of all Socrates, then you will see that is the last diffusive version of minimum residual method. So it's really the one we want to use for wave propagation. And this is the effect of breaking the test functions. You have this additional unknowns, the traces. So here's the first thing that I'm not going to prove, even though the proof is about 2 lines. If the original operator in a strong setting is bounded below the constant alpha, and in the DPG computations, you are using what we call the adjoint graph norm with a scaled L2 part, then this is the insub constant for the corresponding ultra-weak variation formulation with broken test spaces. If you choose beta 0, then you get 1. But then with beta equals 0, you don't have what we call a localizable norm. It doesn't extend to broken spaces, so beta has to be different from 0. And as you can see that it is desirable to have a small beta because then this is sort of negligible and your insub constant is equal 1 or close to 1. Now, what does it mean? Continuity constant is also 1. You can see it from here. That means that the method effectively delivers L2 projection. I mean, and that's for any problem. I didn't say anything about that I'm solving wave problems. There's any problem I formulate that. This is unthinkable for people. When they hear me talk about that, I mean, the first reaction is, and I can see that from their faces and the other, he's cheating. Why is he cheating? I mean, he must be overselling something. I'm not overselling. It is really the case. It is really the case. Now, contrary to standard Galerkin, including Petrov-Galerkin discretizations, watch out for the fact that the discretization now involves not only the original stiffness matrix, the problem, but first of all, the test function, the test inner product. So with different tests inner product, you get different methods. Even with the same functional setting, you can tune things by operating with different test inner products. Right? That's a completely different new concept. But if you think of it in terms of minimum residual method, it's very natural. Because you're minimizing dual residual. So if I change the norm, individually I measure the dual residual. So everything is fine, right? But if you talk to standard engineering community and all they know is, okay, variation problem, put some basis function on it, compute the discrete spaces, the algebra, and be done, then this is a revolution. Because I'm saying, no. You have to tell me what test product you want to use. With that right test product, I get the right stability properties. And then you have the Babushka theorem. With that constant, the best approximation error involves also traces. Okay, so that's the very okay. Okay. Now one extra before I start talking about the actual mathematics. So, what did we do to go from 20 million to 20,000 wavelengths? Well, we use what is called the full envelope approximation. Full envelope approximation is based on the assumption that the solution is represented as an exponential ansatz times a new unknown. This new unknown is not a function of x and y only, it's still a function of x, y, and z. But you're taking this exponential ansatz out. When does it make sense? Well, it makes sense if the departure from the nice uniform wave takes place at the level of many wavelengths. And this is exactly the case for the transverse mode instability simulations. The instability that is created there is related to mode beating, and the mode beating takes place at the level of thousands of wavelengths, right? What that means is that I can put the exponential ansatz corresponding to 1,000 wavelengths, and I'm solving now for a new unknown, but this new unknown, right, varies at a level of 20,000 wavelengths. So I get into, right, the range that I can solve with a supercomputer. Do you understand? So what did we do? We put it into a code. You get what is called a modified Maxwell problem for U tilde. There are extra terms popping out. And we very quickly coded it, and it was a big success story and some recognition from Air Force and so on, but there was no mathematics. All right, so as usual, with some delay, last spring, Markus Mellenk, former student of Professor Babushka and expert on pollution and mathematics of wave propagation, was spending his sabbatical with me for 3 months, or almost 2 months, and I thought this was a good problem for him. So I said, well, we get this weird form of Maxwell equation, let's study it, and let's try to prove that DPG method makes sense for it, because it does. We know it already from computations, right? So to our surprise, what I thought would take weeks or months happened in about half an hour the first afternoon we started talking about the problem, right? And if this is the representation of the operator, this is this major big theorem that we started with. It says that the original operator is bounded below, if and only if this modified operator is bounded below with exactly the same constant. If you remember that stability depended upon alpha and beta, right? And you see immediately here that using the ansatz helps with resolution, because you're now resolving at the level of 20,000 wavelengths, but it doesn't help with the stability. Stability, it is what it is. And here's the complicated proof of that fact, right? Heavily based on the fact that the modulus of E with the purely exponential is 1, because you're dealing with L2 norms, right? So that's the beauty of mathematics and formulations that are based not on coercivity, nothing like this, but boundedness below constant, right? That's what it is. And then, of course, once we realized that, okay, the question was, oh, what can we say about the boundedness below constant for the waveguide problem? So the standard wave propagation, the domain is fixed, right? And you want to study the dependence of the stability constant upon the frequency. And methods that, attempt to have stability and the approximability properties uniform in the frequency are called robust methods. I mean, there has been a fight to invent such methods for a long time. But that's not the case with the waveguide. With the waveguide, the frequency is fixed. It is what it is for the optical waveguide. What you are hearing, though, is the length of the waveguide, the number of wavelengths, right? As our personal experience was, we started with 80 wavelengths and way all the way to 10, 20 million, right? So it's the L. And we started with an easier acoustics waveguide, where things reduce just to Helmholtz equation is a scalar equation. You hit it with separation of variables. You end up with the self-adjoint operator in xy, right? That gives you real eigenvalues, propagation constant in the z direction. You reduce it to stability of the 1D Helmholtz equation in z direction. You use the L2 orthogonality, put it together in about, a couple of days. Marcus and I had this result that the stability constant differs linearly upon the, or inversely linearly upon the length. The larger the length, the larger the number of wavelengths, the smaller the stability, right? And I was so convinced that the Maxwell would be another 2 weeks exercise that last summer I went around and gave presentations about it. Say, okay, so there's the same thing. Well, but in August, we settled down and started to look at the Maxwell, and it turned out to be a completely different story. Very difficult, very difficult. And that's the story that I would like to talk about today. But before I go there, this is the effect of varying beta. I know you're eager to see that. So with beta squared equal to 10 to the power minus 6, half of the digits roughly, this is your sweet spot. This is the best what you get. For up to 256 wavelengths, we're talking 3D Maxwell. You see no pollution. It's L2 projection, as promised, right? But then, if you try to use a smaller beta, random error. You start losing digits. So there's no miracle here. I mean, if I had an infinite number of digits, I would have been able to do the L2 projection all along, but I cannot, right? Anyway, it still makes sense to compute with 10 to the power minus 6 in context of problems that we are solving. We were able to go from P equal 9 to P equal 7, even 6. Right? That's
Is there a relation between beta, maybe Stefan knows, between beta and the order that you used for this? Like if
no, the relation is,
I mean,
the
time
smaller the,
run
no,
this for different orders.
the smaller beta, the better, the better.
I know that, but
stability.
the particular one that is, 10 to minus 6.
I view that differently. The P refinements are here to control effectively the pollution, right?
Sure.
That is the old result. So now you use the best beta you can, and then you control it by raising P. So if you have a nice beta, you don't have to raise P that much.
Okay, you view this.
I should have said that. We always use 2 elements per wavelength, right? And then we figure out what is the necessary order of approximation to do that.
I guess, Socrates, just to add to this, I could have plotted the relation here between P and beta and see sort of like, how much do you need to change P to, accommodate the change in beta. We didn't do that, but as Leszek pointed out, by tuning it in the waveguide problem, we're able to save ourselves about 2 to 3 orders in terms of the order of approximation and get the same pollution error then.
Right.
Yes. Okay.
Yeah. So we knew about the benefit of using the small constant that since the very beginning. I mean, there was a paper or 2 published by Jay's group going back to 2012 or 13, but this was all in context of, solving problems with large ohmic and fixed domain. So now it's a slightly different context, although mathematics input it. Okay, so when we started the Maxwell problem and we encountered difficulties, we contacted our French friends, the specialists from India on mathematics of wave propagation, for good reference. And they came back and said, Marcus, Leszek, don't you know that this is an open problem? Okay. So I'm happy to report that after 5 months of very, very hard work, basically for 5 months, I didn't work on, and Marcus we didn't work on anything else but this problem. We have been able to break through it. And I have more or less half an hour left to give you the main idea about the mathematics involved. So as you will see, the mathematics is classical, but classical doesn't mean easy. It's really involved, okay? So here's the subject, here's the starting point. I'm going to start talking about eigensystems. So first of all, the electric field, right, or the same thing, magnetic field, has three components here, and the first two are combined into transversal field, and then longitudinal field is E3, the same thing for H. And in 2D, we are using these operators, the vector valued curl and the scalar valued curl. And this is the first thing you have to master, algebra behind those guys. Curl goes into divergence, the curl goes into gradient, depending upon how you change things. There's no way you can follow the algebra, the mathematics, what I'm about to present, before you memorize these. So I'm only going to deliver punchline because there's no way you can follow the algebra. The algebra is important, right? Now, so what happens? You take the system of two first-order Maxwell equations, you apply this approximation, it translates into a system of four equations, where now the operators are two-dimensional, and you differentiate between the transversal longitudinal components, right? And then you get this system of four equations to solve. Now, as I said, separation of variables works only for a single equation, so it's out, right? But for the waveguide problems, you can go the other way around. I mean, after all, from separation of variables, right, you end up with a 1D Helmholtz equation in Z for acoustics, and there you learn that there's a propagation e to the power I beta Z. So you can start with that as an ansatz, and if you start with that as an ansatz, you convert the original problem to an eigenvalue problem. Beta is the eigenvalue. This is called, in mathematics, the waveguide eigenvalue problem. And incidentally, this was the first Maxwell experience that I had with the very first PhD student I worked on Maxwell equations beyond Barber-Peggian 25 years ago, right? So that's what you get. So because the derivative in Z is leading to the mass matrix, and you have in the original equations this easy cross, strange thing. So you want to cross it with EZ, and then this curve goes into gradients. That's the starting system of equations, right? And now that you assume the ansatz, exponential ansatz Z, you get your very first eigenvalue problem. Here it is, the system of four equations. The derivatives in Z gave rise to the mass terms on the right-hand side, and you are solving for eigenvalue problem for these four unknowns. Okay? The boundary equations, the boundary conditions reflect, right, the boundary conditions for the waveguide pack boundary on the lateral and on the lateral boundary, right? And the first thing that you're learning is that, okay, this is a non-standard eigenvalue problem. You're missing two mass terms on the right side. The second thing to learn very quickly is, if I look at this left-hand side, it does not represent the self-adjoint operator, even when epsilon is 1, homogeneous waveguide. Oh, by the way, the proof on well-posedness for homogeneous waveguide was well known. It is a non-homogeneous waveguide, which is an open problem, right? Although even in the case of homogeneous waveguide, the dependence upon L was not known. So you look at the adjoint, and there is a corresponding adjoint and a problem, and all I want you to remember is the terminology EH, FG, right? And including transversal and normal components. So, okay, that doesn't look even like a standard eigenvalue problem. It's hopeless. So what do? We eliminate the longitudinal components from these equations. It's begging for that, right? And when you do that, however, you pay the price. And the price is that now you have a system of two, but second-order equations. And it is still not self-adjoint, even when epsilon is 1. So you don't have self-adjointness. So you have to look at the adjoint, and this is the adjoint. And by the way, the functional setting, including boundary conditions, cannot be figure out just by looking at these two equations. It is inherited from the original equation. If you don't study this procedure, this inheritance of dependence between these eigenvectors, we will never get there. This was okay. It took us only 4 months to understand that. Okay, so you look at this and you clearly see you have the gradient of curl that this is not self-adjoint. So you say, why don't I eliminate? Now use these equations that eliminate either H or E and reduce it to a single equation, right? That's the final step. And if you do it now, you expect the fourth order equation because you're dealing with a system of 2 second order equation, but a miracle happens. You don't get second fourth order equation, you stay with the second order. There's a beautiful cancellation of terms. That's the property of Maxwell equations, right? So you get it, you get now individual E problem, and if you eliminate ET, you get the individual H problem. There is no way you can guess this functional setting for this E and H problem without knowing the relation between the succession of these eigenvalue problems, right? And the same thing happens for the adjoint operator. By the way, only at this level, with epsilon equal 1, you hit a self-adjoint operator. With epsilon not equal 1, this is still not self-adjoint. I mean, look at it, right? I mean, you see that the epsilon. But with epsilon equal 1, it's self-adjoint. And after a few months struggling of what to do, we settle for the classical Rayleigh theory of perturbation of self-adjoint operators that he had used to study what? Vibrations of the elastic beam with some damping. Without damping or self-adjoint, he had the damping, okay, he perturbed the self-adjoint. So he was able to do that, right? And the same thing happens for the adjoint problem. You also have these two problems, F and G. And now come critical three lemmas that you have to grasp the meaning of that because there's no way you can control the result. So if E and H, ETHT, with minus omega beta are solutions to the EH eigenvalue problem, then E alone and H alone, the E alone solves the E eigenvalue problem, HT solves the H eigenvalue problem. Minus omega beta is created for beta minus beta square as the eigenvalue. Okay, I already have discussed that, but now it turns out that if you have a solution to the E eigenvalue problem and you define H using the same formula we used to eliminate H, then the pair ETHT, right, solves the EH eigenvalue problem, right? And the key point here is that as you go from beta squared to beta, there are two ways to go, beta and minus beta. Therefore, you get not one, but two eigenpairs. Remember that, because that's going to be a critical piece of information in a moment, right? And the same thing, if you the other formulation, the same thing for the adjoint. And this one comes perhaps as a surprise. Oh, I'm sorry, I'm going to use the blackboard here. So you have the E problem, and you have the H problem, and then you have F, adjoint, and G. Now, for this lemma, thus it indicates the coupling, but along the diagonal. If you take the solution to the E eigen problem, and you rotate the E problem, keeping the same beta squared, then you're getting solution to the G problem. Not F, as you might expect. No, the G. Why? I have no idea. It's just mathematics. Now, the conclusion is that all these four problems, therefore, share exactly the same spectrum. So, right, this is for arbitrary epsilon, variable epsilon. Okay. So, right, try to remember. Succession of eigenvalue problems of decreasing complexity and the critical relation between them, right? And except for the lowest case, I mean, the simplest case of separated eigenvalue problems with constant epsilon, no self-adjointness whatsoever. That's a big difference between acoustics and Maxwell. There's no self-adjoint. All right. So for the homogeneous waveguide, these ultimate problems were self-adjoint. So let's look at the homogeneous waveguide. And as I said, the proofs for that were in place, but even though I'm quite familiar with the literature and the tons of not papers but books on the subject, with pages and pages of Bessel functions, I have nowhere seen this representation that I'm about to show you. So we are looking at the E problem in the case of epsilon equal 1, right? So there's this non-trivial problem involving curl and grad div and a weird functional setting that you cannot figure out just by looking at this equation. But you inherit it from the previous ones, right? And the first thing that I recall is the Helmholtz decomposition. If I take L2 guide, I can always in 2D for a simply connected domain represented as the sum of the gradient and curl, right? Two potentials. And depending upon whether I put the boundary conditions of FEM psi, I can do the same thing for the magnetic field.
Can I ask a question?
Sure, absolutely.
This curl minus grad div, it doesn't end up being some sort of a function?
No, it is not. No, it is, but you will see the relation to the Laplacians coming. That's the big point. So anyway, you take this representation for E that we have and you plug it in there, right? And as you plug it in here, while there's some details that you have to follow, what you obtain is the corresponding Helmholtz decomposition of 0. And because Helmholtz decomposition is unique, therefore you're looking at two zeros here. And these two zeros give you exactly the information that both psi and phi are solutions to the old good Laplace eigenvalue problem, right? So there are three possible situations. You either have an eigenvalue coinciding with the Laplace, the Dirichlet eigenvalue problem, or Neumann, or one that is maybe common to both. That's the most difficult case, right? And this is summarized by this lemma. If beta square is related to a Neumann eigenvalue, the eigenvectors are curls. If it's related to a Dirichlet eigenvalue problem, they're gradients. If it is related to both, if Dirichlet and Neumann eigenvalues for the Laplace are the same, then you get at least two-dimensional eigenspace that contains both curls and gradients. So forget about all these, horrible Bessel and Hankel functions there. This is the structure. This is the whole information of mathematics is sitting, and I could not find it in any book on the subject. So I think we do get some credit for that. The same thing is for the adjoint problem. Okay. First year graduate school example on separation of variables, right? After all, we are now to Laplace eigenvalue problem. You separate variables, you get cosine sine Bessel function. These eigenvalues are either roots of the Bessel functions or the derivative of the Bessel functions. I presume that you have it in your fingertips, right? These are from the web, these roots. And I want you to see that the roots corresponding to J1 are exactly the roots corresponding to J0 prime. When I first copied that, my students told me, oh, you have a typo there. No, it's not a typo. Derivative of J0 prime is equal to J1. So yes, even for the simplest cylindrical waveguide, you do run into the situation that you have two-dimensional eigenspace consisting both of gradients, and it's good to do. Okay, how am I doing with time? 14 minutes. So now things become a bit more technical in terms of algebra, if what I talked about wasn't technical yet, right? So we know that the eigenvectors of the perturb problem are going to be perturbations of these guys. So curls or gradients. So the perturbation is delta E. But of course, you also have to perturb the eigenvalue. The eigenvalue be the square, that's a perturbation, right? And all of these are results of perturbing epsilon.
Is epsilon variable or constant?
Well, in the real step index fiber, it is a variable. But those variations, if you look into physics, they're very tiny. That's what was just. They're of order, 10 to the power minus 3 to maximum 10 to fraction of 10 to the minus 2. That's related to the guiding phenomenon, the limiting Snell's law interpretation. So you plug that into the equation, and you neglect higher order terms, you get a linearized problem for the variation. So I don't expect you to follow the algebra, just the idea, right? Linearized problem. And then the key point here, and this is where credit goes to the Lord Rayleigh, he represented these perturbations in terms of spectral representation of the spectral components and using the original guys that are, after all, eigenvectors of self-adjoint operators, right? So you have orthogonality and all the nice things there, right? And if you compute that, you end up with two equations. One is for the perturbation of the eigenvalue problem, and the other one is for the spectral components of the perturbation of the corresponding eigenvector. So you get these two equations for all cases, except when you're looking at the eigen component. That one is fixed from scaling, right? So these are important details, but I don't think I have time to do about that. But let's look at this equation, for instance. What is it? The perturbation of the eigenvalue is represented in terms of the eigenvalue, right? Corresponding eigenvector, and explicit dependence upon perturbation of the dielectric constant. So there are three terms here. And one of the things for the case of distinct eigenvalues that you can prove is that this perturbation stays real. Okay, I'm not going into details, right? But then, in context of estimation, we have to compute linearized mass matrices. So you're not orthogonal anymore, right? But you're close to orthogonal. So if I want to look at mass matrix EI plus delta EI, EJ plus delta EJ, right? Then this is EI, EJ, and these were orthogonal, delta IJ. But then I have here plus what I call the linearized delta EJ plus EI, delta EJ, and plus delta EI, delta EJ. And this guy, because we're using perturbation theory, is neglected. So all the results that I am about to present are under the assumption that we are neglecting higher order terms, and unfortunately, we cannot claim them to be full mathematical proof, because it's up to those higher order results neglected. Nevertheless, you're getting a lot of insight. So it's sort of applied math proof, if you like, or engineering-like proof, right? But let me tell you, after 5 months struggling with the problem, I was extremely happy to take an honorable exit. So this is what we're computing, and the things that you learn here is that, for instance, perturbation for the codes is actually zero. Not intuitive at all. Perturbation for the graph is explicitly given in terms of epsilon, is the perturb L2 matrix, or mass matrix. And these two are more complicated, but you will see in a moment I don't need them. That also took some time to figure out that we don't need them, okay? Same thing for the curl matrix. So if you compute the curl matrix, you have the same thing. So I'm not going into details. Now, this is the last thing that I hope to communicate today, and this is decoupling of the equations. So how do you utilize this spectrum, in this case of a non-self-adjoint operator, the knowledge about the spectrum, the eigenvectors in the stability analysis? you start with the ansatz, where the solution is expanded into these eigenvectors with unknown coefficients. They're still functions of z, right? You plug it into the original equations, and if you do have orthogonality structure, you decouple the problem into individual problems in z. This is the key point, the reduction, right? Now, we don't have here the orthogonality, right? So it looks at first, okay, you're doomed. That won't work. Well, but if you still remember fundamentals of function analysis, the situation is not entirely hopeless, right? Okay, I'm sorry, I'm still using the whiteboard here. So if you look at not necessarily self-adjoint problem, but a problem that has eigenvalues, and you multiply it with eigenvectors of the adjoint operator, so let's call them EJ star, right? Then the left-hand side is equal to EI A star, EJ star. And this then is equal to mu J bar, EI, EJ star. And you subtract the 2, lambda I minus mu J bar, EI, EJ star is equal to 0. So if these two guys are different, you get what we call bi-orthogonality condition between the eigenvectors of the original operator and the eigenvectors of the adjoint problem. That's why I study the adjoint operator all the time. Right? And that translates into bi-orthogonality here. So you do get that decoupling provided you use the far. Okay. So we do get it at the level of the E problem or H problem. Is that good enough? Not really. Because in order to reduce the original Maxwell equation to just the E problem, you have to do a lot of differentiation. So you end up with a horrible distributional load on the right-hand side of your 1D problem. I cannot go into details. 6 terms. And as you try to analyze it, you get stuck. I mean, the complexity is such you don't do it. Now, I cannot do it with the original problem because it wasn't even the standard eigenvalue problem, right? We're missing the 2 mass terms. So we settled for EH. And this idea came out after several months of looking at the problem that I'm about to present. And that is, okay, so this is this problem that I have here, the second EH problem, and these are the distribution loads you get on the right-hand side by eliminating the longitudinal components, right? And now comes the key point. Oh, this is the corresponding variation problem for the eigenvalue problem. These are the perturbations of ET and HT, right? We have computed them up to the linearized matrices. We choose particular scalings. This is an important detail that I don't have to go into in time. And then we do remember the fundamental result that I in the beginning told you about, and that is that if you take eigenvector to the E problem and compute H with that formula, then the pair EH gives me an eigenpair for the EH problem. When I compute H, I get different H that I get from the H problem, so there's a scaling coefficient here that enters the problem. And when I put it in there, the bi-orthogonality condition is like this. But the key point is, I have a second beta, there's minus beta, and when I change the sign, I get minus d here. So you get 2 bi-orthogonality condition, and that gets into a beautiful decoupling of this EH problem. And then the same thing if beta squared is equal to gamma squared, right? As a result of it, okay, now I know I have lost you. There's no way you could have survived that. But the key point is this has nothing to do with the perturbation theory. By using the very structure of the Maxwell equation in this case, and the adjoint eigenvectors for the individual E and H problem, I end up with a system of first order ODEs for the coefficients in Z, the first order, and they decouple into two subsystems. They involve coefficients, though, right? In the systems involve the eigenvalues, lambda j and mu j, that we earlier have studied. So without the perturbation theory, I cannot deliver for you these eigenvalues. So I cannot make it, but the decoupling is there. It's just that we don't know with what constant. And then comes the estimation, and that's a tough part. So here's the first step. You estimate the L2 term by the sum of the spectral components, and you use the Young inequality in the very beginning to skip the off-diagonal terms. That's the way I said they're not needed. When you don't skip them, you lose 1 month. And you get stuck. There's nothing clear what to do. So in the end, say, why do I worry about them if I can skip them, right? Skip them. And this is where, guys, knowledge about the linearized mass matrices comes into the picture, right? So this is bounded then by these coefficients. Then you estimate these guys. This is where the expertise of Marcus comes in, because he has studied these 1D problems, to that. They're equivalent to 1D Helmholtz problem. And for that, we have very concrete stability results, both for the usual and the L2 and distributional load that you need, because remember, there was a distributional load there, right? And you put things together. Now you can start estimating these coefficients. And when you estimate this coefficient, the Young's inequality again is telling you that you can neglect the perturbation terms. So this estimation is exactly the same as for the homogeneous waveguide, which makes things a little bit easier, right? And in the end, surprise or not, you do get the same result as for the homogeneous waveguide and the same result as for the acoustic waveguide with the dependence upon L, but after 5 months. So that's essentially the end of the story. I have here a commercial yet that represents the work of basically my students, and about the code. I know that you're building your own codes, but both Jeremy and of course Socrates participated in the code. So that's the code I've been building for 30 years. We're looking at the 5th incarnation of that. These pictures are from the 4th version, and the books that we have published, right? And then this is the work of Socrates and the more recent work of Jacob Badger, right? Who is using DPG method to solve problems with up to 12 billion degrees of freedom and 300 wavelengths for 3D bulky domains. This you already have seen, so I'm going to skip to that. This is the work of Jacob. His dissertation is focusing on the analysis of band waveguides. So this is the same problem with the optical amplifier, except that you bend it. If you bend it, the wave is leaving the core. This is, of course, bent with the exaggerated radius, so you can see that, right? I mean, what's the key point here? The key point here is that, okay, in this baby problem, Socrates is telling me this is not a baby problem because it's 500 wavelengths, Maxwell, nonlinear Maxwell, right? Without that activity, you cannot dream about solving. You cannot dream. And this is solved in a matter of minutes, but you need a supercomputer for that, right? The method beautifully scales, and here's the last result that Jacob wanted me to show. It's put into the paper that we submitted. This is seismic modeling, right? And you put the DPG on the DPG solver, and that's how the mesh evolves with the adaptivity, and you build the solution, along with the mesh, very much the same way as Socrates was doing. But we are talking now about problems involving 2 million degrees of freedom, right? As I said, the maximum problem that Jacob has been solving so far is at 12 billion. He's going for 100 billion, and he thinks he can go for a trillion, but I'm not sure about that. Anyway, the message of this DPG story is that contrary to other solvers for wave propagation, DPG beautifully scales in the parallel MPI openMP implementation. And I think if you want to know details, you have to invite Jacob here. And he has a lot to say, including implementation with GPUs and things like this. So otherwise, you have a specialist of the solver. Socrates is here. Right? This is a continuation of the work of Socrates, although we have done some essential new changes, and the understanding has changed a little bit, right? And it's done all using the parallel code that Stefan has developed. Very, very powerful code. We're talking here, if you can solve 12 billion high-frequency wave propagation problem in about 4 minutes on the multi-core, right, multi-compute nodes architecture, I think you should listen. It's not a coincidence. It's really the power of minimal residual methods that display here, right? I'm 1 year away from my retirement, so I'm not selling anything. I don't have to sell anything, but I'm very happy that the work that I've been doing my entire career, is not going to be lost, because the current generation is picking up a big way, and I hope it will survive, and maybe even of some useful labs. I don't know. Okay, that's it. Thank you.
In this result, is this 2D slab of a 3D simulation?
Yes, yeah. You're looking. This is all 3D, full 3D simulation.
And what you showed before were the different properties.
Mm-hmm.
Before you mean what?
The previous lab.
Yeah.
No, this is the problem setting.
Right. This is
Each color here corresponds to different wave speed. This is 3D acoustics, right? So these wave speeds that come from specified in this benchmark you can download, and then he starts with a very coarse mesh, right? That doesn't reproduce the wave structure, and then in the typical DPG mode you start refinements. You can do that because you have stability from day one, and you then produce the right mesh to capture all these non-locally variable.
This is HP refinement.
Those are HP refinements, yes. So it's the usual technology is for wave propagation. You go with H to capture the wavelength, typically 2 elements per wavelength, and then you crank P up. You do need a P adaptive code for that, because this cranking up is local. Not global, it's local. You really need the power of HP adaptivity. But you don't need the sophistication of coming up with optimal HP meshes for this type of wave propagation problems. It's just H adaptivity plus switching to P at some point.
Were these simulations done on the supercomputers at TAC?
That's right. Everything is done in TAC. Jacob now is getting access to DOE computers, so how to solve bigger problems. He's doing. Right, but it is a TAC. On TAC, with a modification to the data structures, he thinks he can do 100 billion on the current TAC computers.
Do you know,
But for
2 billion, how many nodes? Do you assess how many nodes?
Talk to Jacob. I don't remember. Right, because the key point is that you have to talk about data structure, right? So you know how Stefan developed the code by distributing only degrees of freedom, but not the data structure. So that becomes a bottleneck at this level. So Jacob is coming up with the idea of modification to the data structure where he also distributes the data structure.
So information about mesh and it's distributed. It's not
Right. I mean, when you go beyond the 10 billion, you have to start distributing the measure. Up to 10 billion, well, when I say distributed, I mean you have an extremely lean data structure that contains minimal information, but nevertheless, a copy of the data structure sits on every MPI, right, rank. And with that, we can go for 10 billion. But when you go to 100 billion, you have to start distributing even that very lean data. Because degrees of freedom were distributed from day one by step. Right? This is where load balancing comes into the picture. These things are in trouble. You use Zoltan as everybody else. So Stefan already gave you that, right? That's a seminar. So he talked about that.
Stefan talked about his new work when he came here.
In the new work, okay. Right. But he's the one to talk about the parallel version, and Jacob, of course, about the solver. So,
I have a question about the ansatz. So, stability constant didn't change with the ansatz.
no.
Does that mean that if I were to put Galerkin on it, I will not need the fine mesh to have discrete stability, right? I will not need the mesh corresponding to the 2 million wavelengths.
Oh, you would.
Okay, I would, even with the ansatz.
I think even with the ansatz. Yeah, absolutely. I do not. So put it this way. Because, when you are solving the modified Maxwell equations, the modified Maxwell problem, right, is equal to the Maxwell, and then you're getting extra terms. I'm not sure I can reproduce those terms. It's like, I think, the EZ, K, this K, maybe K squared here, times E. So you're getting an extra L2 terms, and I don't even remember the sign. So mathematically speaking, you're perturbing Maxwell with the extra terms. And the more perturbation you have, right, then the bigger pollution error. So I don't know. I have no idea how the Galerkin would behave for this case, pure Galerkin. I mean, but I don't think it will behave better than for the original problem, right? Because the input constant doesn't change.
That's why I asked.
So that means you have to
change.
So in other words, what you're saying is the following: would this ansatz work with the standard Galerkin?
You're right.
The answer is I don't know, but I have my doubts based on mathematics that I do control. Because you're increasing the perturbation gets larger. It contains not only omega but also k squared. Maybe nothing. Maybe it's enough to have to capture this model, but I simply don't know. I don't know. Once you're driving BMW, you don't want to go back to the original. That's my experience. So, he's driving BMW.
Any other questions?
So I have a question about the solver, unsurprising to anyone. So have you tried this DPG multi-grid strategy on anything other than wave problems?
Elliptic problems, no brainer. I mean, so the truth is we haven't done any very systematic study, but Jacob and my postdoc, Ankit, are finalizing the paper where we combine the solver with automatic HP adaptivity that we are resurrecting in context of ultra reformulation, and that is in context of elliptic problems. And the solver works like hell for very adapted HP meshes, including n isotropic.
I can answer this question for the algebraic, AMG and for the DPG work on FEM, where we put it on, it's not the same solver with geometric and HP, but it's the algebraic solvers we have, and you put it on the fusion. It will behave the same as that.
The solver is based heavily on static condensation. So the difference between elliptic and the high frequency problem is that with the elliptic problem, when you build a multi-grid, it makes sense to go all the way down to coarse match of one element and come back to the V cycle. With the high frequency problem, you go down only to the level of the coarse match that satisfies the Nyquist criterion. You may go down if you want, but it doesn't improve anything. Right. You just have to come back, right? But it is because it's a Hermitian problem, it's a conjugate gradient. You don't need GMS, you don't need mean rest. It's a precondition, standard CG solver. So I don't have to tell you that the advantages of CG over GMS in terms of the number of vectors, so on. So this is essential. This is essential.
Because scalable solvers for discussing nonlinear elasticity is something that keeps me up at night. So
my last baby student is tackling nonlinear elasticity. Maybe we need to talk about that. But it's Jaime, right? More of us we work on nonlinear elasticity, but we didn't focus on solvers. It was just trying, the ultra-weak DPG as opposed to standard principle virtual work, and see whether we see any positive effects. And the answer was yes, we did. This was the work partially funded by Sandia. We were able to go to more larger deformation.
yeah,
But this is a work of a poor, graduate student that worked like hell the last year of his study. It has to be systematically developed and so on, and that's what I'm taking up now with Jonathan.
Sure.
Right, so hopefully we'll learn something more there. Talking about this, when you study both theories, you see there is based on the specific relaxation of formulas for the invariants. And the first thing that comes to my mind is, why don't I use the same relaxation in computation? And nobody has done it. And that's what they want to do. For nonlinear elasticity, you have even more choices in terms of variation formulations. So I want to use the one that mimics what is happening in theory. I don't know, maybe it's a stupid idea and maybe nothing will happen, but that's what we can afford in academia, trying out stupid ideas. Right? Just see whether you get something out of it. But it definitely will lead to a PhD, that I can guarantee. It's not tricky, very not tricky. Well, you suffer hour and 15 minutes. All right.
I'll keep asking questions. Is there anybody online?
I don't see any questions online.
All right. Okay, so there's two things. One is the variational form, and the other is the DPG idea. How much of the success do you think is the ultra-weak formulation, and how much is DPG? Or are they the same in your mind?
So, in context of wave propagation with high wave numbers, ultra-weak is absolutely critical. Because of very small diffusivity, it is not as good as for handles, but it's damn close. If I show you for, let's say, 50 or 60 wavelengths, right, 3D problems and compare handholds on a nice uniform match with DPG, you will not see any difference. When you look closer, though, you will see that pollution produced by DPG has a different character than the pollution produced by Helmholtz. Helmholtz produces a phase error.
You mean by standard Galerkin?
By standard Galerkin. And DPG, based on ultra-weak formulation, produces an amplitude, right?
Diffusive.
It's diffusive. The dispersion is still there, but it's tiny, much smaller. So if you're solving problems where
the dispersion error is critical to be under control, it's better than outputs. But the most important thing is that you have a stable method starting with one element. So if you are solving problem where the resolution is not uniform, let's say beam problems like this band, right, where you really need a mesh only to reproduce the solution that is localized, you're saving, huge percentage of the degrees of freedom compared with the uniform mesh that you have to put in for the standard Galerkin just to have stability. Now, the success of DPG is not based, though, on the ultra-weak. And for other formulations, we have other problems where we have used other successfully other formulations. In fact, you can mix them. For instance, and we made a few academic points. There's a paper led by Brendan and Federico that deals with you will remember that sheath problem. Sheath problem, right? It's a rubber. It's a very soft rubber enclosed in a very thin metallic sheath. I mean the ring, right? And the rubber is nearly incompressible. So you're forced to use a formulation that is uniformly stable in the incompressible limit. There are two of them. There's ultra weak and there's a mix, right? But if you try to use the ultra weak for the whole thing, then you suffer from conditioning because this thing is very thin. So they use the standard primal DPG based on the principle of mutual work, and they couple. You can couple different formulations in different subdomains, right? And then you can solve the problem. So I mean, it's a little confusing, if you're working with the standard principle of mutual work and you have just one variation formulation to worry about, right? Then things look kind of simple because there's one path to follow. Now with DPG, you have multiple paths. You have to do first your homework to choose the variation formulation that will work for you. And once you choose the functional setting, you still have the room to manipulate the inner product. I haven't talked here about, wonderful ideas that we have tried and never pursued in terms of papers. You can scale those inner products in such a way that you emphasize residual in a specific subdomain. And then you're getting like a zoom. I want the solution to be good here. And adaptivity will focus on that subdomain. I tried it. It worked like hell. So you have unprecedented, flexibility of this methodology.
Yeah, I understand. I understand that.
I mean, you pay the price. Now, what is the price? I mean, you're solving normal equations, right? So it's like least squares. The condition is still 1 over a squared, but you have doubled your number of unknowns.
It's the memory. The memory is one of the biggest prices, particularly on modern architectures. You cannot get even local matrices in high order. So these focal inverses become significant challenge. But I understand that it's a trade-off.
You get adaptivity from there one.
Yeah.
But yeah, like with these squares, right? So I simply believe that it's a matter of investment of time and human power, right? And you can break through any technical. When people try DPG, right? I mean, you remember the story of higher order methods. When the higher order methods came up and people tried to use codes that were optimized for P equal 1, then perhaps 2, to solve with P equal 5, well, they said this is absolutely hopeless. Nothing works here, right? Because conditioning was killing them, the solvers were slow, the integration was forever. It took a decade or so to develop sensorization, right? The fast integration, to develop to understand how to construct high order shape functions to control the condition number, and how to build solvers that utilize it, right, to see the power of higher order methods. And now in context of GPU, what I'm hearing about is all about higher order methods, right? Nobody questions higher order methods anymore, right?
Here.
Not here.
In other places, people do.
Right, but you know, it's what I'm trying to say is that you build a new technology, you have to invest, because you cannot put the new technology into old frame. It's like, right?
So I do want to follow up on my question.
Yeah. Okay.
So I understand that both things had to happen for this problem. In other fields where DPG, in your opinion, has made a difference, how often did you have to also change the variational formulation? Or are there examples where there's a field, elasticity, in diffusion, there are many other ways to do the elliptic problem?
Okay. So
where you just brought DPG itself.
So my usual comment at this point is the critical thing here is anticipate the regularity of the solution, right? If you are, why is the ultra-weak DPG so good for wave propagation, especially for wave propagation in space-time domain, right? I just came back from Oberwolfer meeting in March. It was all dedicated to space-time formulations. Why? Because if you're solving wave propagation model in space-time, you are propagating discontinuities. It's all about discontinuities. The solution is discontinuous. I mean, let's remember D'Alembert solution, right? You're propagating discontinuities. If you're propagating discontinuities, the only formulation that survives this low regularity is ultra-weak. You don't have a choice. You go with the ultra-weak, right? Because of discontinuities. Now, other problems is the same story. Depending upon how irregular is your load, initial conditions, whatever, some formulations, come to the front as more natural choice. But I don't think you can come up with the general idea that this works and this doesn't. No. It's a new powerful methodology, not so new, it's already 15 years old, but methodology where you can play and you have to, for your particular problem, you have to choose one. So I would have a different philosophy. That's what we have in our code, that we support any, variational formulation in context of DPG implementation, any. Because I can take any well-posed variational formulation, break the test functions, introduce extra variable traces, and I have all the system, the code, the structure, the infrastructure to discretize those problems. So it's more like embracing it than picking to just. That's my philosophy. But otherwise, every nonlinear problem is a problem on its own. Which you have to understand, which you have to study, which you have to. This took us 6-7 years.
This is so nice. It will be, but it's like, for example, Livermore, it's not a particular problem of interest. It's not one of the main problems.
Right.
Well, that's why I'm wondering if we can apply this same abstract thinking and methodologies to the problem.
I'm trying to connect it to a problem.
Well, we tried the Tokamak.
Well,
it's a horrible.
Is still an external problem.
It's still an external problem. Okay. So I don't know. We get the closest to what Jeremy is doing. We're nonlinear elasticity, but I started nonlinear elasticity really only the last few.
Yeah,
few years.
That's why I'm asking.
Yeah. So this is one has to try. I mean, okay, the situation of a poor university professor. I mean, you attach yourself to a funding agency that is willing to fund you, right? So in our case, it turned out to be a great relationship with Air Force. Yeah. And the partners we have in the high energy. I mean, I didn't mention here the name of Jay Grossek, our partner from. Without him, nothing of this would have happened because he took painful 6 years to educate us about nonlinear optics. And if you're a civil engineer and mathematician like me, it's very far away from nonlinear optics, believe me. But as you dig in, all these mathematical perspectives open up, and you learn that there's more and more math, not less and less, but more and more math that you can do and that is useful. So I'm very pleased because whenever I talk to these laser people, and these are people that do mostly physics and, high big computations, they always appreciate very much the mathematics behind it.
That's what we want. We want math that is useful.
That is useful.
But
yeah.
ideally, maybe not for this classes of problems, maybe for nonlinear elasticity. I don't know, nearly incompressible elasticity robot solvers.
Oh, that's easy. I mean, for linear elasticity, that's well understood. That's not an issue.
It's still nonlinear.
But nonlinear, different, yeah.
Yeah, nonlinear is still,
Yeah, nonlinear, we have to, yeah, well. There's, what can I say? Well, you have to start supporting a little bit the work at the university on that, and you'll start moving in that direction. I mean, it doesn't happen overnight. I mean, these two guys can tell you how many years it takes before they understand what I'm talking about. Although the two were very fast, but it still takes 4 or 5 years to raise a mature PhD student. I mean, it doesn't happen overnight. It's a systematic process, right? And what I have to tell you, one of the exciting things that these problems, we talked about that with Socrates yesterday for half a day, taught me a lot of mathematics, new mathematics. I thought I had known, but turned out that no, I had no clue how things expand.
So Klaus, I remember that years ago when you talk about DPG, you would do the confusion problem.
Right.
So can you kind of comment in terms of like if you compare like a DG type discretization from convection?
May I have your attention, please? Today's emergency response Pillar Building 368 has concluded. Thank you for your participation. Repeating. Today's emergency response Pillar Building 368.
I gotta go, but we can.
Thank you for your participation.
Okay, so I haven't given up on confusion problems, but as I was telling Socrates this morning, the disappointing thing is that the 5 versions of minimum residual based methodology, I tried on that, and I didn't go into 3D, it was only into 2D, but also space-time with true magnetics. It stops at 10 to the minus 5. I know for compressible gas dynamics that I know something about, right? Compressible dynamics stops. The meaningful number is 10 to the minus 7. And my dream always has been that I build a compressible dynamics stops code where I put the problem in, push the button, and I see what I see here, right? With adaptivity, resolving boundary layers, interaction with the shock, and so on. Mm-hmm. And I can do it, but for 10 to the minus 5. I cannot write this number 10 to the power 5, right? I cannot do it for 10 to the power 7 because I'm losing digits. And I would need a quadruple precision, and that's not competitive. So I don't claim, to be extremely competitive in that area. But I think if you talk to people that do the DG for living, I mean, for this type of problems, you should talk with Jesse Chan. I will also work on DPG, and he is one of very few people that have experience with both. Or my postdoc, Karen Ankit, who also used DG and DPG. Then you will see that the final word is still there. So the DPG has this fantastic pre-asymptotic stability, right? With DG, the performance is very much based on stabilization. You have the right stabilization, right? It works beautiful. And the destabilization is mesh dependent. Something that works asymptotically may not be optimal in the sense in the pre-asymptotic region they are over diffusive, and there are a lot of things to learn still.